All right, good morning, ladies and gentlemen. This morning, we are going to look at your half sheet from Thursday covering acid-base introduction, specifically pH and conjugate pairs. Looks something like this. All right, there we go. So I had some of these problems on it. You guys watched videos over it on Thursday while I was gone. Oh, thank you. Anyway, so we're going to go over how to do and tackle some of these problems, and we'll look at a few more as well. And what I showed you at the beginning of class is this quarter sheet that you can use for the quiz and assessment next week. And it just outlines all of the equations that we were taught last week. And so with these equations, we're going to go with, if we look at number one, we'll see the information we're given and the things that we're trying to solve for. These are best to be used. If you memorize these equations from working with them, that's a bonus, but because I'm giving you the quarter sheet, it's not necessary. The trick here is, can you apply them? Can you use them if you're provided them, and show that you can do the work as a result? So let's take a look at number one. All right, so for number one, it says you're given a pH of 12.3, and they want you to find the H plus concentration. They want you to find the hydroxide concentration, and they'd like you to find the POH concentration, or the, not concentration, but what is the POH? So we've got A, B, and C. These problems is it doesn't matter what order you go in, okay? Because you're able to get to any of them from any equation at any time. So if we'd like, we can start off with A, just going in that order. We want to find H plus, and we're given pH. So which of these do you think would be best to use? The second to last, this one? Yep, this would be the best because we want to solve for H plus and we're provided pH. So we can do 10 to the negative pH equals the H plus concentration. And that means 10 to the negative 12.3. And when we put that in our calculator, we're going to do, where's the button? So it's the inverse log. So see where the log key is right here? If you look right above that in blue, it's 10 to the x. So we'll do second log, which gets us 10 to the, put that on here. Okay, and we put in negative 12.3. And the answer that we get is 5.01 times 10 to the minus 13. So that is going to be our concentration of H plus. And we put M for molar with it. This number does make sense because if the pH is 12.3, does that mean it's acidic or basic? It means it's basic. So if it's basic, which means it's not very acidic, a very low H plus concentration. Because H plus, if it's very concentrated, then we have a low pH, which says it's acidic. But if the pH is high, then we're basic, not acidic, so the H plus should be low. Okay. So there's our answer to A. Now, do we want to do B or C next? You want to do B? Okay, so to do B, if we want to find hydroxide, which equation is going to be the best one to use, do you think? Based on the information we have. So the last one requires us to know pOH, which we can use this one if we solve for pOH first, which we can. So we can go in that order. Right now we know pH and we know H+. So we could use the first equation, and that would allow us to solve for hydroxide. We can do that. So if we have H+ times hydroxide equals 1.0, I guess just 1 times 10 to the minus 14. If we divide both sides by H+, we get 1 times 10 to the minus 14 divided by H+, which above was 5.01 times 10 to the minus 13. So on the calculator, which I'm not sure if we can see that on the screen, 1 times 10 to the minus 14, which the way you like to do it is 1 times 10 caret negative 14. Notice I put that all in parentheses so I don't mess anything up order of operations. And then divide that by, in parentheses, 5.01 times 10 caret negative 13. And the answer that we get, 0.01996, which is about 0.02 molar. Right? And so now that we have figured out our hydroxide concentration, we can find pOH. So pOH is the negative log of hydroxide, which means that we are doing negative log of this 0.02. So, and for my sake, I still have that number in my calculator from the last problem. So I'm just going to do negative log answer. And we get a pOH of 1. Comes out about 1.70. Okay. Now, if we want to check ourselves, I'm not doing this to confuse you, but just to show you that there's multiple avenues of solving for these problems. So what we could have done is remember above that pH plus pOH equals 14. We were provided a pH of 12.3. So if we plug that into that equation, then pOH would come out to what? What's 14 minus 12.3? 1.7. Yep. Okay. So we could have solved for pOH because we were given pH. That's one way. And then Kylie had said before to use this bottom equation to find hydroxide concentration. We could do that. You know, we could have taken the inverse negative log. So invert 10 to the negative 1.7. And that would have come out to about 0.02 molar. Okay, so all I'm trying to show you here is it doesn't necessarily matter which order you do the problems in. They're going to get to the same answers eventually. Okay. How are we feeling after that one? Better? So let's look at number 2 then. Does the black show up better than the red? Good. Okay, so for 2, it says you're given a proton concentration, H+, of 2.8 times 10 to the minus 7. And they'd like us to find the pH, hydroxide concentration, and the pOH. Okay, so right off the bat, probably solving for pH is going to be the quickest one to do, because pH is equal to the negative log of our H+ concentration. So negative log of 2.8 times 10 to the minus 7 comes out to 6.55. That's the pH. Did you guys get that for pH? Yes, I hope. Okay, so based on how we did number 1, what would you like to solve for next, hydroxide or pOH? Or, yeah, hydroxide or pOH. Which one? pOH? Sure. So I'm labeling it C, but I'm doing it out of order. So pOH, we know from what we're given, pH plus pOH equals 14. We know that our pH is 6.55. So if we plug it in and solve for pOH, what do we get? Okay, 7.45. Okay. And then for B, you want to find hydroxide. So your best bet here is the inverse negative pOH, which is our hydroxide concentration. And I say it's your best bet because we just solved for pOH, so we can plug that in right into the calculator. And what we get, I'll put it in the scientific notation, 3.55 times 10 to the negative 8 molar. So that's the OH concentration. So by the way, if you hadn't gone that route and you're like, hey, I want to do B before C, and you want to find your hydroxide concentration, keep in mind that H plus times hydroxide is 1 times 10 to the minus 14. So you could have gone so that hydroxide is equal to 1 times 10 to the minus 14 divided by our H plus concentration, which was given as 2.8 times 10 to the minus 7. Plug it in the calculator and solve, and we come out to, in this way it's actually 3.57 times 10 to the minus 8, which you might think is a lot different than what we saw up here, but at 10 to the minus 8, we're talking like 0.0000000002 difference. Is that very big of a difference? No. Therefore, it doesn't matter which direction we go in. You could have done this route to find hydroxide first, and then if we take the negative log of that, we end up with 7.45. Tyler. Just for concentration. Or when you do pH and pOH, the unit kind of disappears.
For the 10 to the pOH, how do you solve for them?
in the calculator?
Yeah.
Let's see where you can best see it. So do you have a scientific TI? So if you do second log, you see that's like 10 to the, and then just put in negative whatever your value is. So in this case, we would put in negative 7.45. And it comes out to that really small number. So I just switched it to scientific notation to get more precise. Okay, so that was 2. Let's pause for a moment from calculations and go look at conjugate pairs. So number 3, write the conjugate acid for hydroxide. And for B, carbonate. So when we're finding the conjugate acid, what are we doing fundamentally here? Like how are we finding the conjugate acid? What are we doing to it? Adding how many? 1. Add 1 proton. So here's how I like to think of it. I'm going to add H+. I'm going to do kind of math in a sense. So I have OH plus H. What do you think that gives us for a formula? H2O. And what happens to the charge? We have a -1 and a +1. When we add them together, you get no charge, 0, right? So our conjugate acid for hydroxide is water, H2O. Okay. For B to find the conjugate acid, we're going to add H+. Okay. So you have CO3, and we add an H. So that's going to give us HCO3. And then what's the charge going to be? Just negative, right? Or -1. Because you had a -2 and we add a +1 to it. So we get -1. Okay, so that's conjugate acid. If you can show the H, I'm happy. Generally, because we're going conjugate acid, the H's always go in the front. Okay, so for conjugate acid, we add H+. For conjugate base, we remove or subtract. So for 4A, you have NH4+, that's ammonia. This time we're subtracting H+. So what does that end up with? Okay, we have NH3, because we had NH4. We took an H away, so now we're NH3. And we had a +1, and we subtract a +1, so now we're neutral. Okay, for B, we have this formula here. If we want to find the conjugate base, we subtract an H+. So what happens, so what do we have for the formula part here? We have this, we take away an H, so what's left of the formula? SO3. And we had a -1 charge, and we subtract +1. So we got -1, or -1 minus 1, which ends up with -2. So SO3 -2, our sulfite ion, is what we end up with for the conjugate base. Okay, so does this make sense? Conjugate acid, like, it's the result of the base accepting a proton. So effectively, if we show it this way, we say, what's the conjugate acid? We add an H+. And then the conjugate base is the result of the acid donating the proton, or losing it, which means we look at the base, we look at the acid, and we remove or subtract an H+. Okay, because it had donated it, so now we get the basic form. Okay. For 5, you have the following equation, HNO2 plus water, and they're showing it as a reversible reaction or at equilibrium, probably because nitrous acid here is a weak acid. So we're going to see this week that if it's weak, it's going to set up an equilibrium. We're not going to do anything in terms of calculations with the equilibrium, but just identify what it means. And then we make NO2 minus and hydronium. So based on this equation here, can we label the acid and the base as well as the conjugate acid and conjugate base? And by can we, I mean do it. So let me put it this way. If I look at the reactant side, I have 2 things that start with H. Now, as the teacher and having experience, I know which one is the acid and which one is the base. But from the student point of view, it might be difficult because they both have H, and we see the acids start with H. No, on the reactant side, remember, we can go to the product side and figure out the conjugates. So if we do that over here, which one is the conjugate acid, which one's the conjugate base? Yeah, hydronium is going to be your conjugate acid. It has the H. Remember, our acids are going to have an H. The NO2 minus has no H, therefore it cannot be acidic. But if it's not acidic, it means it's the base. So we label it as conjugate base. So based on that information, HNO2, is HNO2 an acid or a base? It's the acid, right? Because the acid donates the proton, and the result without the proton is the conjugate base, which means water is the base because it accepts the proton and becomes the conjugate acid. So all I'm doing in explaining which one is which is just using the definition of conjugate acid and conjugate base. Okay, we got 2 more here. So for 6, explain what happens to each of the following as the pH of a solution goes down. So pH goes down. Before we answer any of the questions about this, if pH goes down, does this mean we're acidic or basic? Or I should say, if pH goes down, are we becoming more acidic or more basic? More acidic. Okay, I don't know what the exact value is. So if we gave exact values, maybe it is basic still. But the idea of the trend is if it's going down, we're becoming more basic, less, let's say basic, more acidic, less basic. Right? So with that information at our disposal, and less basic, what happens to the hydroxide concentration? Does the concentration of hydroxide ions go up or down for more acidic? Down. Oh. Hydroxide is going to go down because if we're more acidic, that means that we have more H plus around. So B, H plus concentration should increase. If it increases, we're more acidic, that's a lower pH. Okay? If we are more basic, then we should have more hydroxide around, right? So then pOH, well, if our pH goes down, remember that pH plus pOH equals 14. That's always at equality. So if the pH here goes down, what happens to pOH? It goes up. And notice that concentration and pH, or hydroxide concentration and pOH, are inverse. And it has to do because mathematically we're doing a negative log. Lastly, number 7 says a neutral substance is equally acidic and basic. Explain this statement. What do we think is going on here?
So I was thinking like a neutral substance is like in the middle, and so since it's like neutral, it doesn't have any more amounts of like acid or base.
Okay. So the neutral, we're saying that pH is, I'll say it's 7, which means it's in the middle, right? So you said that we don't have more say it again?
Like we don't have more amounts of acid. Or more.
Okay. Don't have more H plus versus hydroxide, right? So the H plus, our proton, is the acidic part, hydroxide is the basic part. So we don't have more amounts of one versus the other. If we're equally acidic and equally basic, then what that means is that H plus is equal to hydroxide concentration. And if we know pH is 7, we could do the inverse log of the negative pH, which would tell us that our concentration of both would be 1 times 10 to the minus 7. So they are the same value in terms of concentration. We don't have more of one than we do of the other. It's neutral. Okay. Any questions up to this point? All right, so how about this? Let's turn to another page. And I'm going to give you another pH problem. There we go. So for this one, given pH of 3.5, what is H plus concentration? What is hydroxide concentration? And what is the pOH? And even though I've labeled these A, B, and C, you can do them in any order that you choose.
So all your ratings that you have to use, which will go out.
Yeah, he went out there last week. So he was out there for about 10 days visiting. Yeah. So he spoke in San Diego, but then he went down to see his picture. Only so he was really like this sort of like out there. I think it's been pretty excited about that out there.
Part of the stuff like this, but it's equal.
Oh, my mom. So like I didn't see it right now. It's like,
All right, folks, so remember, we're still live right now. This is a ridiculously long video. So if you're watching this again later, you can skip like the second or towards the end there, you can skip a bit until we talk again. But if we're looking here, if for A to find H plus, if we do the inverse log of the negative pH, what we come out to is 3.16 times 10 to the negative 4 molar. Okay, in your calculator, you probably didn't have scientific notation, so it was 0.000316.
yeah.
Okay.
Can we round on that, like 3.2 times 10?
Sure. No more than that.
Yeah.
For B, some of you went the direction of doing H plus times hydroxide equals 1 times 10 to the minus 14. And if you did that and you plugged in H plus, which was from above 3.16 times 10 to the minus 4, what you came out with was 3.16 times 10 to the minus 11. And then that was for hydroxide concentration. And then pOH is negative log of your hydroxide, which from what we just did above would be 10.5. Okay, what you could have also done is said that pH plus pOH is equal to 14. And so 14 minus 3.5 would give us 10.5, which is the same as that. And then you could have done inverse log of negative 10.5, and that would have given you that value right there. All right. Tomorrow we're going to learn something new, but keep refreshing on this. We'll have another warm-up to start class tomorrow. Quiz on Wednesday.